welcome to the lecture on structural damping and equivalent viscous damping. We have already discussed the forced vibration response of a system, single degree of freedom system having viscous damping, and then we discussed in the previous lecture the Coulomb damping, and we found that to deal with Coulomb damping, we calculated the equivalent viscous damping, and then we used the same equations that we derived in case of viscous damping. So, as I said that the energy dissipated in one cycle can be equated for different type of damping, and equivalent viscous damping can be obtained, and that can be used in the differential equation and the amplitude response that we already have obtained in some lectures. So, today we are dealing with structural damping. So, what is structural damping? So, we can recall that structural damping, when we load some material and then unload that material. So, the stress strain diagram that is different in loading and unloading. So, there is some loop that we can see here. There is a loop formed when we load it and when unload it. So, means in loading we give the energy, but during the unloading we do not get the same amount of energy. So, where does the difference of energy goes? So, this difference of energy is expanded in the molecular friction of the material. So, this concept of energy dissipation is used as damping, and that is called structural damping or solid damping or material damping or hysteresis damping, because here the loop that is formed is called the hysteresis loop. So, from the experiment it is found that the energy dissipated per cycle in hysteresis damping is proportional to the square of the amplitude, while we saw that in case of the viscous damping the energy dissipated per cycle is pi c omega x square. So, we can write, so we see that the energy dissipated per cycle for viscous damping is pi c omega x square. However, energy dissipated per cycle for hysteresis damping or solid damping it does not depends on the frequency, but so it is like pi h x square. X is the amplitude of the response. So, here h is hysteresis damping constant, okay. And we can define beta, and beta is h by k is hysteresis damping factor, where K is stiffness. So if we have a system that is, so we show the hysteresis damping in this way. So this is M, K, and this is, let's say, beta. So we represent H or beta, and this system is doing some motion here, and it is subjected to some force F0 sine omega t. Okay. This we can see here, that is the same system. Now, as I said that we have to convert this system to a equivalent viscous damping system, so that we can use the derived equations and the formula of the response. So here we can equate the energy dissipated per cycle. So energy dissipated per cycle pi h x square. That is the energy dissipated per cycle in the hysteresis due to hysteresis damping, and we assume that we have to know the equivalent viscous damping. So in a viscous damping, the energy dissipated per cycle is pi c omega x square. So we want to know what is the C equivalent. So C equivalent is the viscous damping that is equivalent to the hysteresis damping. So we can find C equivalent here. So here these will cancel out some terms, and we will find C equivalent is h by omega, or because h is k times beta, so we can write beta k by omega. So this is the equivalent viscous damping corresponding to the hysteresis damping. Now this system we can represent to an equivalent viscous damping system. So here we can write it is like K and viscous damper. We can show a viscous damper. This is mass K, and here it is C equivalent, and that is equal to beta into K by omega or H by omega, and this system is subjected to F0 sine omega t, and this is the response of the system here. Okay. So as we can make the free body diagram on this system, this is here it is F0 sine omega t. Here are the spring force K into x, here C equivalent into x dot, and this is x double dot. So we have already we can write the equation of motion, that will be mx double dot plus C equivalent x dot plus kx equal to F0 sine omega t. So we can write mx double dot plus C equivalent is beta k by omega x dot plus kx equal to f0 sin omega t. So for such a system with m, c and k, we already have find the response of the system. So the solution of this equation, let's say equation 1, will be steady state solution. So here we say steady state solution x equal to x sin omega t minus phi. So here, as if we recall, x equal to f0 upon k minus m omega square whole square plus, now here c is c equivalent, so c equivalent into omega whole square under root. So because this formula we have already derived when we discussed the forced vibration of viscous damp system. So there were stiffness and viscous damping and mass elements of a single degree of freedom system. So these equations are as we discussed how we achieve this equation. So this term we can write f0 by k, because we can take here k outside, and this is 1 minus m omega square by k whole square plus so C equivalent into omega by k whole square. So let's write this like f0 by k upon 1 minus omega square, and k by m is omega n square, so we can write omega n square upon whole square plus this we can write 2 zeta equivalent into omega by omega n whole square under root. So what is zeta equivalent? So zeta equivalent is nothing but C equivalent by Cc. Cc is critical damping, and we know that Cc is equal to 2 root k into m, that we have already derived. Now C equivalent is beta k by omega, so we here write. Now if we compute this term 2 zeta omega by omega n, so this is zeta equivalent, so 2 into C equivalent by 2 root km into omega by omega n. Now 2 into C equivalent is beta k by omega, so C equivalent is beta k by omega, so we write beta k by omega into 1 by 2 root km into omega by omega n, and omega n we can write root k by m, So it is root k by m. So here 2 is cancel out, omega is cancel out. Here m cancel out, and root k it is k, and k cancel out. So it's come to equal to beta. Okay. So we can write equal to f0 by k 1 minus. So let's say omega by omega n equal to r, as we have already used this type of representation. So 1 minus r square whole square plus here 2 zeta equivalent omega by omega n is equal to beta. So we can write beta square and then under root. So here x by f0 by k equal to 1 by 1 minus r square whole square plus beta square. Okay, so this is the response amplitude of the system having the hysteresis damping. Now we have to find the angle phi . So angle phi, as we know that phi equal to tan inverse 2 zeta r 1 minus r square. So it is equal to tan inverse 2 zeta r is beta, so beta upon 1 minus r square. Okay. So this is phi. So from here we can find this response. We know x, we know phi. So this response is obtained. Now we can see, because this response is function of this beta and r is nothing but the ratio of the excitation frequency and the natural frequency. So we can have this plot of amplitude ratio and phase angle. So we have plotted this x by f0 k on the y axis and r, that is omega by omega n, on the x axis, and for different value of beta, means different value of hysteresis damping factor, we have plotted these graphs, and we can see that these graphs, so if we put here r equal to 1, this is maximum, and that is 1 by beta. Okay. So here we see that when r equal to 1, we are getting the maximum amplitude for any value of damping, any curve of any value of beta. So the response is increasing when omega by omega n is less than 1. So it is increasing till 1 omega means till the resonance frequency, and then it becomes maximum at resonance, and then it is decreasing and tending towards 0 when we are increasing the omega by omega n value. Okay. Now when we see the phase angle curve, so what we see that in this phase angle curve, we see that when r equal to 0, it is tan inverse beta. Okay. So, means that this curve starts with some phi greater than 0. Okay. And so, the force and the response x, they are never in phase. And they all passing through the phi equal to 90 degree for any value of damping, and finally when we increase the value of omega by omega n, they are tending towards the phase of 180 degree. So, now we will discuss one problem that is based on this theory. So, let us take one numerical example. Okay, so we can see the problem here, numerical example. So, a load of 5000 Newton resulted in a static displacement of 0.05 meter in a composite structure. So, there is some structure, some composite structure, and when we apply a load of 5000 Newton static load, so we find a static displacement of that structure 0.05 meter. Then a harmonic force of amplitude 1000 Newton is found to cause a resonant amplitude of 0.1 meter. So, here it is said that so let us write. So, here F static equal to 5000 Newton and X static equal to 0.05 meter. Now, it is said that a harmonic force of amplitude. So, let us say that harmonic force F equal to F0 sin omega t. This is our harmonic force, and the amplitude of the harmonic force. So, F0 equal to 1000 Newton. So, this is 1000 Newton, found to cause a resonant amplitude of 0.1 meter. So, here it is said resonant amplitude. So, what is resonant amplitude? So, resonant amplitude means when the excitation frequency matches with the natural frequency, means excitation frequency is equal to the natural frequency of the system. So, means here omega is equal to omega n, and at this frequency of forcing, the x, that is the amplitude of vibration, is 0.5 meter. So, x equal to 0.5 meter. Now, what we have to find? We have to find the hysteresis damping constant of the structure. So, hysteresis damping constant we have to find, and we have already defined what is hysteresis damping constant. Then we have to find the energy dissipated per cycle at resonance. So, what is the energy dissipated per cycle in the resonance condition? Then the steady state amplitude at 1/4 of the resonant frequency. So, if the excitation frequency is 1/4 of the omega n. Okay, so we are in the region of less than omega by omega n less than 1, and the steady state amplitude at thrice the resonant frequency. It means omega equal to 3 times omega n. So, we are in the region when omega by omega n is greater than 1. Okay. So, we have to solve this problem. So now the first thing is that if we have, suppose we have this system, so this is m k and this is, let's say, beta, and this is f0 sine omega t. Okay. And we have to, so here we have to find the stiffness k. How we can find k? From this information, as it is said that if we apply 5000 Newton, the displacement, static displacement is 0.05. So k equal to F static upon x static, because stiffness is force upon displacement. So we have 5000 upon 0.05. So we can find, we can solve it, and we can calculate it. 5000 by 0.05 equal to, so it is 10 power 5 Newton per meter. So this is the stiffness K. Now we have to use, because we are given x at omega equal to omega, and we have to use this formula x by f0 by k. So x by f0 by k equal to 1 upon 1 minus r square whole square plus beta square under root. Now when omega equal to omega n, that is, this means that r equal to omega by omega n equal to 1. So if we put r equal to 1 here, we will find x by f0 by k equal to 1 upon, so 1 minus 1 is 0, so we will have beta square and under root beta square, so we will get 1 by beta. Okay. So from here we will get beta equal to f0 by k into x. So we get beta equal to 1 by x, and this is f0 by k. Now what is f0? So f0 is 1000 Newton. So we have 1000 Newton. K is 10 power 5. So this is 10 power 5 into x. X is 0.1 meter. 0.1. So we will get, so this is 10 power 3, 10 power 5, so it is 100, 100 into 0.1. So we have 10, so it is 0.1. So we get 0.1 beta value. Now we have to find the A part, the hysteresis damping constant. So what is hysteresis damping constant? A. So hysteresis damping constant is H, and H is beta into K. So beta is 0.1 into K. So K is 10 power 5. So we get, it is 10 power 4 Newton per meter. Okay, so we have got the part A. Now we have to find the energy dissipated per cycle at resonance. So, energy dissipated per cycle, we have already found this formula of ED per cycle. So, ED per cycle is pi h x square. So, pi is 3.14 let's and h equal to 10 power 4 and x at resonance is 0.1. So, into 0.1 square. So, from here we can find, so it is 0.01. So, we can find 314. So, it is joule. Okay, so this is the energy dissipated per cycle. To find the steady state amplitude at 1/4 of the resonance frequency, so C part, we have to put, so here omega equal to omega n by 4, this means that R equal to omega by omega n equal to 0.25. Now, if the value of R we put here and the value of beta what we obtain here 0.1 we put here, we know f0 the magnitude and k we have already known. So, we can get x from this formula. Similarly, in case D we have omega equal to thrice the omega n. So, 3 times omega n, this means that R equal to omega by omega n equal to 3. So, similarly, in similar to case C, we put R equal to 3 here, beta equal to 0.1, f0 equal to 1000 and k equal to 10 power 5. So, we can also get the steady state amplitude x. So, we complete this part. So, thank you for attending this lecture and see you in the next lectures.